all of these different techniques for factoring. We have learned how to factor the greatest common factor. We have done factoring by grouping when we see four terms. We have learned trinomial factoring and factoring using U substitution. Our last technique in section 5.3 will be to factor a difference of squares. Well, first we need to learn to recognize what a difference of squares is. So the beginning here of this section will teach us that you must have two expressions where the signs are opposite. And the terms are perfect squares. First, we need to identify or revisit what perfect squares are. Let's just look at numbers. 1, 4, 9, 16, 25, so on and so forth. These are perfect squares because all of them can be found by taking a number times itself. 2 times 2, 3 times 3, 4 times 4, 5 times 5. Now, variables to be perfect squares have to have powers that are even. X squared, x to the fourth, x to the sixth, and so on. Even powers are divisible by 2 and equally split into the same expression twice. X times x is x squared. X squared times x squared is x to the fourth. Now, if the above are true for A and B, that we have opposite signs and perfect squares, then this is the definition of a difference of squares. So a difference of squares is x squared minus y squared, and that can be factored into x plus y times x minus y. So you get two binomial factors where the only difference is one is plus and one is minus. The factors look exactly the same except for the sign. So we're going to begin practicing this technique. So here's a couple of hints. First, always look and watch out for the GCS. And make sure that you factor the polynomial completely. Let's begin. 25x squared minus 4. I see opposite signs and perfect squares. There is no GCF, so I'm going to show two sets of parentheses. And I'm going to use what number I could use twice for 25 and 4. So I'm going to write 5x plus 2 and 5x minus 2. Let's continue. The next one, 16c squared minus 49d squared. I see opposite signs and everything is a perfect square. No GCF, so I'm going to write two sets of parentheses. I'm going to use 4c twice for 16c squared. Plus and minus, and then be careful, this has a d squared on the end, so I'm going to use 7d times another 7d in the other parentheses. And I have factored that difference of squares. 64m to the fourth minus 4y to the fourth starts out with a GCF of 4. I'm going to factor it out. Now inside my parentheses, I have a perfect square number and powers that are divisible by 2. So I have a difference of squares. 4 will stay in my answer. And I'm going to write two sets of parentheses. I'm going to write 4m squared plus y squared, 4m squared minus y squared. Now when I get to a binomial that has the same signs, it's no longer factorable. This one is done. But if I look at the second one, I have opposite signs and I have perfect squares. So this is a factorable binomial. It's another difference of squares. When we factor difference of squares, we must be careful to look to see if any hidden difference of squares come about. If so, we have to factor completely. The U-try problem, does it have a GCF? It does, of 5. Is what's in the parentheses a difference of squares? You would ask yourself, are the numbers perfect squares and are the powers even? I would say yes. So I'm going to factor this. Notice everything in my parentheses is identical except one's plus and one's minus. Alright, let's look at some difference of squares that are appearing to be a little bit more complicated. But I bet there's a technique that we have already discussed that might help us. I would say what holds us back on problem 4 is that multiple expression a minus b. Well, how about we use u substitution and take it out for a minute? So I'm going to replace a minus b with u. Now I see a much simpler binomial that is a difference of squares, and I will factor it. Remember, when you're using u substitution, you must finish by replacing u with what you had it represent. So I'm going to put back in my a minus b. Let's try again. On problem 5, what would u represent? Would it represent r plus 2t? And now rewrite this binomial with u instead. So I would have 49 minus u squared. Now we typically don't see the variable second, but does this satisfy the criteria for a difference of squares? Does it have opposite signs and are both parts perfect squares? I would say yes, so it is factorable. This is where students mess up though. The expression is starting out with 49, so that's what we must work to multiply to first. So our parentheses will start with 7. They will then be followed with plus u minus u. Now it's the u that has to be replaced. Notice when I was using minus u, I put r plus 2t in parentheses because this binomial expression is all behind subtraction. So to finish, I have to distribute my sign to both r and 2t. And I have my factored answer. The bottom of this page is now a hodgepodge, and it challenges you to know what technique to apply. Remember, first always look for GCF. Then ask yourself, how many terms do I have? If I have 2 terms, I'm going to look for a difference of squares. If I have 3 terms, I'm going to factor by trinomial factoring. If I have 4 terms, I'm going to factor by grouping. Let's take a look at number 1. There's a GCF here that I'm going to factor out first. Now what's in the parentheses are 2 terms. So I'm going to check, is it a difference of squares? I have squares and I have opposite signs. There is my final factored answer. 2. Again starts with a GCF of the same as 1, 2a. But what's in my parentheses is not a difference of squares because I do not have opposite signs. So we said a binomial that carries the same signs is no longer factorable. This 2a is all that I can factor. Moving on to 3 and 4. We see that they are trinomials. Let's start by finding GCF. So if I take out 5, I get 16z squared minus 8zw plus w squared. I now have a trinomial that I'm going to try to factor. So remember, this is FOIL factoring. I am unfoiling the trinomial, so I need to multiply first to 16z squared. I know here that this is positive, which means my signs are the same, both negative, so I can throw in minus signs. And if I need to multiply to w squared, I'm going to use w. Now you have to check for the middle, so you find your outside, inside. So my outside is negative 4zw, and my inside is also negative 4zw, which makes negative 8zw. Problem 4 begins also with a GCF. So I took out 3p squared and wrote p squared minus p minus 30. Now that trinomial inside those parentheses I'm going to factor. P times p would be p squared, and I'm looking for how to multiply to 30 and get back negative 1 in the middle. Well, negative 30 means my signs are going to be different, and I know that I could make 6 and 5 do this. Problem 5 is a trinomial, but it has an x plus 3 expression running through it. Too big for us to leave, so we're going to use u substitution. So I'm going to swap out x plus 3 everywhere with u. Now I'm going to factor this trinomial. So I need to find a way for 10. I'm going to try 5 and 2. I also need to multiply to 5. Well, the only way to do that is 5 and 1. Remember what we said earlier in class. I can't put 5 with 5 because they're divisible by 5. So I must put 5 over here with 2u. My negative on my 5 means my signs need to be different. So plus and minus have to go somewhere. I got to make sure I get this 23 also, so let's see. My outside value would be 25, and the inside would be 2. Well, if I had a positive 25 and a negative 2, I'd get back 23. So here's my minus on my 1 and my plus on my 5. Now I can't box out this answer and say I'm done because I still have u. I must go back and put in x plus 3. So I'm going to distribute and simplify and be finished. 5x. 5 times 3 is 15, minus 1 is 14. 2x. 2 times 3 is 6, plus 5 is 11. And there is my final factored answer. Problem 6 is not a trinomial. It is a 4-term polynomial, so we would factor this by grouping. I like the order it's in, so I'm going to leave it. My first two share x to the 4th. My second two share a negative, so I'm going to factor out negative 1. Remember, factor by grouping is going correctly if the binomial you see is the same. So x plus 3 is now my common binomial factor. I'm going to factor it out. And I'm going to group together x to the 4th minus 1. Now you would expect to be finished, but this is going to begin to happen. X to the 4th minus 1 is a difference of 2 squares. I have opposite signs and I have perfect squares, so I must factor this further. So x squared plus 1, x squared minus 1 is what I would use. And then I have to look at it again. Remember, binomial factors that carry the same sign are finished. But this one on the end has different signs, and these are squares again. So it factors one more time. I am now finished.